Welcome to another video of our course in probability theory. Last time we introduced these different kinds of convergence that random variables might have, which were almost true convergence, convergence in probability, LP convergence, and weak convergence. And in the next video, we are going to discuss pairs of them. In this video, we will cover almost sure and convergence in probability and how they're connected. Okay, let's get right into it. So, let's get started. Almost true convergence and convergence in probability. Let me remind you of this general graphics that is also in the manuscript. So we are today dealing with the left part here. So almost true convergence, convergence probability, and our main result today will be this proposition 7.6 here, which shows that if a sequence converges almost surely, then it also converges in probability. And if it converges in probability, there is a subsequence which converges almost surely. But before we can come to this, we need an auxiliary lemma, which is the following. I call this here a characterization of convergence in probability because there is an alternative formulation. So xn goes in probability to x. So to write that down, what did this mean? That meant for all epsilon bigger than 0, the probability that Rxn, x bigger than epsilon goes to 0. So that was the definition. And I claim here it's equivalent to say that the expectation of, well, the same difference here, this here is minimum. So if you don't know this notation, well, side note A, this here is minimum of A and B, such that this here is 1 if the distance here is bigger than 1, or it's the difference if that's smaller or equal to 1. Which, for example, means that 1 here is a dominating function for this thing here in the expectation. And this here goes to 0 if and only if xn goes to x in probability. And as you see here, so the definition of this here requires always to pick some epsilon bigger than 0. And on the right-hand side, we do not have this. So the epsilon we do not need here on the right-hand side. Which means that it's maybe practical to, in some proofs, to use the right-hand side here. So let's come to the proof. There are two parts, from left to right and then from right to left. From left to right. So pick some epsilon bigger or equal to 0. And then I need to show, given this here holds, also this here holds. And this is the same as the limit is smaller than epsilon, because epsilon is arbitrary. And how to do this? Limit of expectation difference xn, x minimum 1, n goes to infinity. Well, I say this function here is smaller than epsilon plus the indicator that Rxn x is bigger than epsilon. Because okay, the easy part, if the difference here is bigger than epsilon, then this here, the whole thing here is bigger than 1, and this here is at most 1. And if the difference is smaller or equal than epsilon, well, this function here is epsilon, and this function here is smaller. So I could say, I could exchange this or bound from above the expectation over this by the expectation over this here. and this here is epsilon plus the probability that r xn comma x bigger than epsilon. The latter here goes to 0 by the assumption, so by n going to infinity, this here goes to epsilon, and we are done, because I've shown that the limit here is smaller than epsilon, and for all epsilon, so it has to be 0. Okay. Then from right to left, that's also not too hard. That's just the Chebyshev inequality. The probability that r xn comma x bigger than epsilon is smaller or equal than, well, the expectation of r xn comma x divided by epsilon. And if I use here 0 smaller than epsilon smaller than 1, I can also add minimum 1 here, because this here is bigger than epsilon if and only if this here minimum 1 is bigger than epsilon, if epsilon is smaller than 1. So like this. And since we're proving from right to left here, this here converges to 0, which means the whole thing here goes to 0 when n goes to infinity, and we are done with this proof here. Okay, very nice. So what remains to be done is the main result, which we want to prove today. Convergence in probability is equivalent to saying that there is, for every subsequence, there is another subsequence, such that along the subsequence you have almost sure convergence. So there's a typo. AS stands for almost surely. Okay, so there are two things we need to do. So first, from the first to the second. So I know convergence in probability, and I need, for every subsequence there is another subsequence. So take a subsequence, and for the subsequence I know, of course, that the expectation of r xnk xk minimum 1 goes to 0, which means that I can find another subsequence nkl such that it doesn't only converge to 0, but it's summable. Yeah. So find another subsequence nkl such that the expectation of sum L from 1 to infinity R x n k L. Sorry, this is not an xk here, that's just an x. Comma x, minimum 1. Which is, of course, the same as the sum over the expectations, L from 1 to infinity, R x n k L x meaning 1. This here is smaller than infinity. And now I have this here. So this here converges to 0. Okay, that's for sure. Anyway, so this here converges to 0. What else can I say? So this here is summable, which means this here is also summable. So this has a finite expectation, which means that this thing here goes to 0. Because I have a random variable, which is a sum over things, which is finite, which means that these things here have to converge to 0 almost surely, essentially. So write it down like this here. So there's a random variable, which is the sum here, which has a finite expectation. And remember, that means here, that means that the random variable is finite almost surely. X, N, K, L, X, minimum 1 is finite. So this probability must be 1 on the one hand. On the other hand, if I have numbers which are summable, that means their limit is 0. So their lim sup. N goes to infinity. R, X, N, K, L, X minus minimum 1. Okay, that's 0, and this is 0 if and only if it's 0 when I forgot about the minimum 1 here. Yeah, and this of course because the probability is small or equal to 1. So I have 1 small or equal to 1, which means all things here in this inequality chain has to be 1. In particular, this here has to be 1. And this here is the almost true convergence of x, n, k, l to x. Okay, so that was the first direction. And now we need the direction, so this from 1 to 2, from 2 to 1. I'm going to show the following. If 2 holds and 1 does not hold, then I construct a contradiction, which is the same as to show that 1 follows from 2, because, well, 1 follows from 2 is 2 or not, 1 or not 2, and it's just a proof by contradiction to say that this here is the same. So if 2, it cannot be that 2 holds, but 1 does not hold. So let's assume 2 and not 1 holds. Because 2 holds, typo here, because 2 holds, no, because 1 does not hold. So that's why I have to start, because 1 does not hold. Xn does not converge to x in probability, which means there is an epsilon. No, that means, so, okay, so this does not hold here, which means this here does not go to 0, so there's a subsequence which converges to something bigger than 0. So take nk such that the expectation r x nk x minimum 1 is bigger than, the limit is bigger than 0, like this here. Then I have a subsequence. Since 2 holds for this subsequence, there is another subsequence such that we have almost sure convergence. So on the one hand, if we have limit n goes to infinity, so k goes to infinity, expectation r x n k x minimum 1 here, this here is bigger than 0. On the other hand, we have a subsequence, another subsequence, such that xn goes to x. Which means along the subsequence, this here converges to 0. Just a moment. So this here, I say the difference xnk and x minimum 1 is on the one hand bigger than 0. But even more is true. I think I have to be a bit more specific. So this limit is bigger than 0, but just to be sure, I can also take an epsilon bigger than 0, and the limit here is bigger than 0. So like this here, I can also say, because the limit, well, the lim inf is then also bigger than 0, like this here. And the lim inf is certainly smaller or equal than lim sub, say, L goes to infinity, expectation R x n k L, x minimum 1, because the lim inf here, well, that's the smallest subsequence that you have to take, and that's smaller or equal than the subsequence xnkl, which we have here, so like this. So we now know this here converges almost surely to 0. It has a dominating function, which is 1, which means we can exchange the expectation and the limit, which means this here is 0. And now we have a contradiction, because 0 cannot be less than 0. Okay, great. And that means we are done, because that shows 2 implies 1. So we have shown today the left-hand side here. And in the next video, we will show the right-hand side here. Connection of convergence probability and LP convergence. See you then.